computer. Yeah. Okay. So, good morning or good afternoon, everyone, and welcome to the Center for Theoretical Physics weekly seminar. Today, it is a pleasure to welcome Tim Atherton from Tufts University in the US. Tim did his PhD at Exeter University in the UK, after which he emigrated to the US, where he's been since. And today he's kindly agreed to tell us about some of his latest work on liquid crystal films. So before I hand over to Tim for the truly interesting stuff, a couple of announcements from me. First, this seminar is being recorded. So by staying on, you're giving consent to your voice and image being recorded and stored. Second, in the interests of internet stability, can I ask everybody except the speaker to mute their microphones and switch off their cameras during the seminar. If you wish to ask a question, you are of course free to unmute yourself and switch on your camera if you so desire. So without further ado, it's over to Tim now.
Thank you so much, Paolo, for the kind introduction, and thank you for the invitation to speak before this audience. Obviously, it's a strange product of the pandemic that we are now able to draw speakers from a much wider place, but nonetheless, I very much hope to meet all of you and sometime to visit beautiful Portugal on this rainy and cloudy day in Boston. I'd far rather be there. But it's my great pleasure, if you give me one moment, to talk to you about some of my latest work on spontaneous topography in thin liquid crystal films. One moment. It's working. And this is actually I'm largely going to be talking about work that has just come out in Phys Rev Letters. You should be able to see the link on the top right-hand side. It just came out a couple of months ago. I will pause in a few places to offer you the chance to ask questions. If you also want to post them in the chat, we can look at those periodically as well. So very good. So for those of you, I think there's a great deal of familiarity with liquid crystals in this group, of course, but just in case anybody is coming to it a little new, just a brief collection of reminders. So firstly, nematic liquid crystals, which are something I'm going to be talking about a lot. These are fluids. They can flow like a liquid, but they have orientational order. They have long range order like a crystal. They're composed of rod-like molecules. The molecules are relatively rigid. They form an ordered phase with an orientation. So the molecules tend to prefer to align in some direction. And I can characterize that, or one way I can characterize that is through a unit vector field known as the director. So I've just illustrated that. Let's talk about, because I'm going to talk about these somewhat peripherally. They're not the main focus of the word, but I just want to make sure you know what they are. There's another kind of liquid crystal called a Smectic liquid crystal that not only has orientational order, but it also has a layered structure. So the molecules form a periodic density wave, as you can see with this schematic on the left. One thing that's good to note here is that the liquid crystals are greatly restricted by this layered structure. The layers are a molecule or so's length in length, that is a few angstroms. They're very nearly incompressible. And so something that comes out of geometry is that the space of configurations that are available to them, the space of layered structures that have this layered constant layer spacing, there are only a few surfaces that meet this, and I've shown them on the right. Some of them are pretty obvious: planes, cylinders, spheres, tori, but there are a couple that are maybe quite new to people. One is something called a Dupin cyclide, and the other is a parabolic cyclide. In any case, All this is to say that smectics are greatly restricted in their configurations by the presence of the layering. Now let's talk about some other properties of liquid crystals, just so everyone's on the same page. Well, one of the properties is that they possess anisotropic elasticity. That is to say, different kinds of deformation cost different amounts of energy. So here is like a canonical slide that I think is probably in most liquid crystal talks. We have here 3 types of deformation, and they're called splay, twist, and bend. There's another kind of deformation that if you look at one of my relatively recent papers, we've done some work on measuring, but I won't talk about that today, called saddle splay. That's a surface-like effect, and we're gonna ignore that here. One thing that again is sort of illustrative of the difference of different types of liquid crystal is that the nematic can adopt any of these configurations, or it's totally okay to do that. In the smectic phase, however, these twist and bend deformations are forbidden. They're incompatible with the constant layer spacing, and so they tend to be excluded. Now, one other thing that I probably should have put more emphasis on, because it's going to be very important, is that we often talk about the anisotropic elasticity in the liquid crystal field, but we often don't talk so much about the anisotropic surface tension. And what I mean by that, surface tension is, of course, the cost of increasing the size of an interface, and the point is that energy, that surface tension, can also be orientationally dependent. It can depend on the orientation of the liquid crystal at the interface. Another kind of piece of physics that I'm just going to make sure we're all on the same page with is that, because of this ordering that liquid crystals have, there can be special points where the orientation is no longer continuous. These are called defects. And the presence of these defects and the type is a very powerful way to classify the phases that we get. If you look down a microscope and see particular kinds of defect, very often this is a signature of the type of phase that you're seeing. So they're very useful objects to know about. Now, I could say that there's really a lot of research over the years. Here are just a very small number of cool examples whereby we're ordering liquid crystals in some sort of confined, some sort of container. We could be putting them on a sphere, we could be putting them in a channel or a bubble of some kind. All sorts of things happen. One thing that happens is that the geometry can be kind of incompatible with the preferred order. Like, the liquid crystal wants to adopt a spatially uniform state. The geometry rather doesn't let it. And so you get all sorts of interesting patterns, spontaneous emerging structures. These are all very cool. Some of these are smectic, some of these are nematic. But, this has been a very long established trajectory of research looking at how confined liquid crystals spontaneously adopt all sorts of interesting configurations. Now, a more recent trend has been to look at what I would call shape-shifting liquid crystals. So ones where the container or the boundary can change. One example material is something called a liquid crystal elastomer. These are rubbery polymeric materials with a liquid crystal component that's sort of locked in by the polymer. And these can, in response to a stimulus, it could be light, it could be electric fields. These can change shape very dramatically. They're very cool. They're very cool, like elastomeric materials. Another kind of situation is because, as I said, liquid crystals can have anisotropic surface tension. In contrast to a regular fluid, where the shape of a droplet of a regular fluid ends up being spherical because that minimizes the surface tension given a volume constraint, there's no such thing for liquid crystals. They can actually depart from that things. So we can get like non-spherical, non-circular liquid crystal droplets. These are called tactoids. If I have time, I might show you a little bit later. So that's kind of another thing to know about. Then another area that has been tremendously interesting to people is something called an active nematic. These are materials that have internal dissipation. They are driven, like crowds of people kind of thing, because of the activity, the dissipation, these have the possibility to deform the container that they're in, of course, as well. And so there's a very famous picture here showing them do exactly that. Some other examples are, so-called vesicles, like thin shells made out of nematic or smectic. These can also spontaneously change shape. It's pretty neat. Pardon me, with smectic liquid crystals, as I was saying, this layer constraint can be very significant. And one way that the system can kind of have the configuration that's energetically reasonable is to start deforming the boundary. And that's something that's been observed quite extensively in smectic liquid crystals. So all of these are examples of a liquid crystal system that is either variable in shape or is able to change shape. The shape is kind of a part of the minimization problem. And what my group really tries to do is to develop numerical and analytical methods to kind of understand shape change, I guess I would say. Liquid crystals are one system we work in, but I think that's the one I'm going to talk about here. So I'm going to show you, it sort of depends on the time, honestly. I'll certainly show you one, I might show you 2 to 3, but I'm going to show you the new work, the spontaneous topography above patterned surfaces. And if there's time, I might show you a couple of other things that we've been doing as well. But I guarantee we will finish, in a nice amount of time. So let's go with the main menu item, and that is, again, so here's a conceptual kind of thing to think about. So if I have a pond, right, a pond, a pool of water, a lake made out of regular isotropic fluid, whatever is happening at the bottom of the pond, has really no influence whatsoever on what is happening at the top, because in an isotropic fluid, information about the bottom cannot be transmitted across the fluid because isotropic fluids cannot transmit elastic torques. Right now, certainly we can have things like waves. We can have all of that, and nonlinear waves, actually can be height dependent. But just in the static case, if I do a pattern on the bottom of a pond, no image of that pattern happens on the top. There's nothing. Now, in a liquid crystal, because we have this possibility of transmitting, elastic distortions, it's possible, at least in principle, for a surface pattern to transmit a distortion elastically across the fluid that then results in a shape variation at the top. And that's what I'm going to talk about. That's really what I'm going to talk about today. So that's sort of, again, if you don't get much else out of this talk, that's really what we're talking about. And that is, how can information on one side of a liquid crystal produce a shape deformation on the other? I showed you this a little earlier, and that is to say that, this is something that happens pretty routinely in smectic liquid crystals, because, the layer constraint, and, here I'm showing you a sort of example smectic configuration called a focal conic domain. When we kind of have these, together, they have quite expensive elastic defects in the middle of them. And, to reduce the energy cost of those defects, they can induce a surface undulation, which actually can be measured. This paper on the right uses an atomic force microscope to get that. So it's quite ubiquitous in Smectics. It's much rarer in nematics, and that's what I'm going to talk about today. Now, actually, we can go back to the very famous physicist de Gennes, who really championed the soft matter field, I think, and certainly liquid crystals. And actually, in one of his papers that I think is somewhat maybe underread or underappreciated, he actually talks about defects in the liquid crystal assembling on an interface. You produce these defects either by a magnetic field or imposing what are called hybrid boundary conditions, boundary conditions where the orientation at one side is different from that at the other. And what he shows in this paper is that the these defects form a square lattice, and it's a really lovely result. It's actually only relatively recently been observed experimentally, and it was a beautiful paper that I recommend in Soft Matter. This group, Donkey Yoon and Dan Bella, observed this exact kind of. You can see it's a little messy, but I mean that's what you get. You can see that they've observed this this lovely spontaneous assembly of a square lattice of defects. Again, the crucial piece of this is that the defects are on the same side as the interface. So information isn't being transmitted across the film. This is an elastic interaction of defects that leads a deformation on the interface. So I'm going to show you something a little different, but this is a valuable kind of starting place. I'm going to start by showing you the experiment and then kind of building a little bit of analytical theory. So the experiment is this. So how we got interested in this is my work by my experimental collaborators at Case Western Reserve, is they were interested in producing something called an oily streak texture. This is something that happens for Smectics in very thin films. The film here is like, submicron. I told you that Smectic structures have to be assembled out of certain bits, certain surfaces. Here they're coming from bits of cylinders, hemicylinders really, and kind of bits of planar structure that kind of join together, and you end up with like a periodic array of hemicylinders. So that's called an oily streak texture. And what my collaborators wanted to do is they wanted to try, like, what happens if we try to bend it? Like, can we bend it perturbatively in the direction, in the long direction? And so the way they did that is that they patterned the surface. They abuse something called an atomic force microscope, which is a device that kind of normally for measuring topography. Here, if you bring the tip into contact with a soft polymer film, you can actually align the polymer chains, and that imposes a local orientation. So here are two patterns they made, what I'll call an azimuthal pattern. That's where they kind of dragged it round to make circles, and what I call a radial pattern, where they scribed radial vectors. And they also did like the opposite pattern on the outside for some reason. That's not going to be so important, but that's something they did, just to be clear. I want to emphasize this because I think this picture could have been a bit misleading. Like the size of the pattern is very large. It's on the 100 micron scale. The films that I'm going to show you are very, very thin. They're going to be submicron. So the aspect ratio here is ginormous, right? But I want to make sure that you're aware of it. Okay, so they do that. Here's the radial pattern. Here's what the microscope image looks like. You can see you get oily streaks. They form kind of concentric circles, and it's really very nice indeed. So that looked good. But then they did something, they said, well, okay, let's have a look at the topography, and particularly as we cool it down. So they start, rather than kind of, this is what you get in the Smectic phase, but if you heat it up and look at the nematic phase, then we have, the nematic phase is actually completely compatible with these boundary conditions. On the upper surface, the free interface, the nematic will just be vertical. On the planar surface, the one that's been scribed, it'll just try to follow the pattern. The liquid crystal director tries to follow the pattern, as I'm just showing you schematically here. So the point is that both of these configurations in the nematic phase will induce a point defect on the pattern surface and leave a basically vertical interface on the free interface, on the interface that's open to the air. And they will, what will happen, what they try to do is they try to measure the topography of that free interface, not only in the Smectic phase, but also into the nematic phase. And so this is the big result, is that way above the Smectic phase, well in the nematic phase, already we get topography, right? Like we get like what looks like a hill. Now, again, it could be very easy to be misled by the axes on this. So again, I want to stress this, the X and Y axes, that is the pattern axes, are in the hundreds of microns. The topography is very small. It's only a few nanometers, but nonetheless, it is meaningful. It is meaningful topography. It's certainly easily measurable with the AFM. So we have, a rather beautiful effect whereby a pattern induces a distortion in the nematic that then produces somehow topography. And that's what I'm going to try and convince you how that topography arises. Before I do that, let's kind of have a look at the temperature dependence of this effect. So if I start on the right-hand side of the plot in the isotropic phase, no topography. I cool into the nematic phase. I start getting topography, as I go, and as I cool further, the topography gets bigger and bigger and bigger. And eventually, when I get into the Smectic phase, it starts becoming kind of pointy, and there we go. Right. So the sharp central peak emerges below the nematic Smectic transition, but well into the nematic phase. Then what they did, this was just before the pandemic hit us, but we managed to get enough data to publish, which is good. We were looking at different film thicknesses. So one of the things that we found is that as you went to a thicker film, the topography went from being kind of more dome-like to more cone-like. So that's something. And then one other thing that I just want to stress is that the topography only happens, it only shows up for the radial configuration. For the azimuthal configuration, no topography at all, right? So that's sort of really the physical effect, and that's sort of the experiment is, we have this spontaneous topography showing up above a pattern surface in the nematic, and it shows up for one pattern, but it doesn't show up for another very similar pattern. So let's try to figure out why that is, what's driving it. So one thing that's definitely happening is that the two kinds of pattern involve different types of distortion. So here I'm just showing like a cross section through calculated structures in the nematic with a fixed interface. For the radial one, that's the one on the left, it turns out that only splay and bend is going on. Whereas for the other one, for the azimuthal one, there's also a lot of twist. So that's one thing that's happening. And we can assume that the interface is rigid. We can actually even analytically produce structures for this, minimizing structures for this problem. And this is what they look like. That's what I'm trying to say. So now, let's now consider the full problem. When I say minimizes, I should tell you what energy I'm trying to minimize. This is the energy I'm trying to minimize. It has elasticity, the terms I showed you earlier, and then it has interface terms, including the isotropic surface tension, and also what is normally called the anchoring term in liquid crystals. This is a term that favors the alignment of the liquid crystal, the director, with a preferred axis that I've denoted here, NE. It's usually called the easy axis. And normally we think of it in this way, and I'm going to kind of highlight it because it's really important. Normally we think about it in this way. We think of it as, yes, we have this, we have this preferred orientation, the easy axis, NE, on the surface, and the liquid crystal would like to align with it, but there may be a cost if we deform it away, right? So we think of it as the surface commanding the liquid crystal what to do. But actually here, the exact opposite can happen, right? I'm kind of reversing the causality, because imagine the liquid crystal is fixed. It already knows which way it wants to point. Then in fact, actually, the surface could shift as well. So it's kind of we often talk about it as the surface commands the liquid crystal, but in actuality, it's a bidirectional relationship. Equally, the liquid crystal could command the surface. So I think that's kind of a nice thing to think about. I can build an analytical model. I'm going to not spend too much time on this because I think you probably, but it's a very simple one. I'll use cylindrical coordinates. I'll parameterize the free interface in cylindrical coordinates. Once I have that parameterization, I can construct the surface normal on the free interface. And I can also parameterize the director similarly in polar coordinates. It's a bit confusing because I'm using cylindrical coordinates for the position in space, but then I'm using a spherical parameterization of the directors. So yeah, don't worry too much. Now, if I substitute all of this sort of ansatz into my energy, what I find is that the anchoring term kind of actually is quite revealing to look at it. There's a coupling you can see between the topography and the orientation. So the topography is entering through the derivative of the height function, and the orientation is all of these angular variables, theta and phi. And we can see that this coupling has kind of emerged. We can also see it vanishes in a few cases. One way it can vanish is if the director is vertical. So no coupling then. And also it vanishes if the director is purely azimuthal, and that's going to be a big clue for us in a moment. So that is to say, we get a coupling between topography and orientation in the radial direction, and no coupling in the so-called azimuthal direction. And that, that will help us explain why we see the topography in one orientation and not in the other. Now, what we can do is we can try to minimize the energy, and we'll do that by linearizing the solution about a flat interface with a known director profile. We'll just assume that we know the director profile. I can, crank through the math and produce an Euler-Lagrange equation for this situation, which is quite pleasant. The boundary conditions I'll impose is that the height function should have, it should be flat at the top, and that it should also be flat at some specified boundary, L, right? I'm also going to impose a volume constraint as well. And, I have available, I have a very nice kind of ansatz for the pre-specified orientation. I can get that from something called conformal mapping. this is a very nice and quite rare example, I think, of a situation where we actually can get an analytical solution. So here at the bottom is a nice analytical solution for the height profile. It doesn't mean that much currently. I have to solve for the boundary conditions. They're just very messy. I didn't do those here. But when I do that and plot it, you can see that the solutions really do look very like the experimental setup. So we get these nice hills, and as we increase effectively increase the thickness here, we do in fact converge on this nice cone shape as was experimentally observed. Moreover, the decoupling that happens in the azimuthal case means that we get no topography whatsoever for the other kind of pattern, as also was observed experimentally. So I want to kind of, again, step back and just kind of re-articulate what the new effect here is. Well, the new effect here is what I would call anchoring mediated topography. That is to say, we have an elastic distortion on the fixed interface. It produces a spatially varying director on the free interface. And, you know, under favorable conditions, which really means kind of a fairly thin film, you know, favorable anchoring energies and the like, induces a topography due to this sort of coupling between interface and orientation in the surface anchoring term. We can use a computer program that I've developed that does these minimization problems numerically with finite elements. You know, we can get interface shapes that look similar. So now we got rid of, you know, I showed you a very, very simple linearized theory. This is minimizing the energy functional, you know, with very few assumptions, but only numerically, of course. And that's nice because, you know, we can compare with the analytical work. Here I used a slightly different boundary condition. Actually, I didn't use the zero derivative boundary condition. I kind of fixed it at the other side. And we can actually probe which of the energy terms are, you know, what are the forces acting on the interface? What is the relative contribution of the energies? And I think this is the sort of really, really nice, because you can see this analysis, what this analysis is showing is that it's the anchoring and the surface tension, that is to say the isotropic and anisotropic components of the surface tension, that are setting the topography. The elasticity is kind of a mediator. Without the elasticity, we wouldn't get the distortion of the director, but it's not actually the dominant term in the analysis, unlike in the de Gennes case that I showed you earlier. So let me just summarize before I give you a little very brief sort of tour of some of our other related work. You know, our model predicts that we've got topography that shows up in the nematic case. It's due to a competition between isotropic and anisotropic components of surface tension. We get it in one case and not the other because there's a coupling that vanishes in the latter case. We get increasingly cone-shaped topography as we increase thickness that we also see through a linearized analysis. And I guess I should also say we've done some numerical work that is still kind of ongoing to understand this more fully. So here might be a good place to just briefly pause and just see if anyone has a question. I can pull up the chat. No one has chatted, but would anyone like to ask a question already? It's a good place for a pause.
Okay, so any questions? If you have any questions at this point, can you raise the little hand? Don't see any little hands.
No problem.
No,
okay, so
okay.
Okay, did you have one, Paulo? Sorry.
Oh no, sorry. I was just going to say you can carry on.
Very good. So I'll just give I'll give a very quick kind of tour of another problem that's closely related. And that is these tactoids, non-spherical droplets of liquid crystal. You know, these are kind of something that have been known about for a very long time. It's a different sort of liquid crystal. These are lyotropic liquid crystals. They are functions of concentration, not temperature. But they've been observed for a very long time. You know, since the foundations of the field, I guess. You can also get, interestingly, you can get isotropic inclusions in a liquid crystal droplet. These are called negative tactoids. And all sorts of really interesting things happen. They can be like aligned. They don't have to be spherical. It's pretty neat, actually. So tactoids are kind of fun things. Now, there's been a recent explosion of papers on tactoids, actually. I should probably put some citations here, but up until very recently, like there was relatively little work on them. They're quite challenging to model. You can do it computationally with something like a Monte Carlo simulation, but obviously these are necessarily limited in scale. You can do like a sort of a simplified ansatz calculation. That was a very productive line. You know, so quite challenging things to model. And what my group had been working on is, you know, as part of our work on shapeshifting, was a way to do so. So, you know, the energy is actually exactly the same energy as I showed you before for the other problem. It has elasticity, it has anchoring, surface tension, it has area constraint, it has a volume constraint. I guess I'm doing 2D here, so it's an area constraint. And we also have like liquid crystal orientation. We also have to have a unit vector constraint as well. And what we can do is, using our finite element code, we can find explicit minimizers of this energy. We have a lot of very nice features. One feature is it's adaptive. So the computational effort is directed where the energy the energy density is highest. We have like an automated regularization scheme that keeps the mesh quality uniform. And you know, the short story here is that we have a very good way to find minimizers of liquid crystal tactoids. You know, a different energy. Yeah, so in fact, here's a slightly different set of parameters, and you can see it's becoming much more pointy there, because the surface tension, I guess, is the anchoring is higher. And so what we can start doing is mapping out, you know, as a function of the line tension or the anchoring energy, we can map out the different shapes that you can see. If the anchoring is relatively weak, the liquid crystal ignores it, and so you just get like a normal circular bubble. As we go to higher and higher anchoring energies, we get elongated shapes that could be almost kind of like a lozenge, a kind of a rectangle. Some look a bit like lemons, which is kind of fun. We can map out this space of possible configurations. And in fact, actually, there was some prior theory that had predicted where different shapes might emerge, and we kind of see all of them in kind of roughly, well, in the right place. But we can do this quantitatively and getting explicit minimizers. We also reproduce the experimentally observed shapes pretty well. Because unlike, you know, anyone else previously, we're able to use different starting conditions. And so we're also able to get negative tactoids, you know, with like interior voids. We can see how they interact. You know, I think this is another kind of very nice thing that we can do. I'll maybe just show you the final one, because I think it fits in the theme so well, and I think we have a little bit of time. You know, the third the third kind of example that I wanted to just briefly talk about is to say, well, you know, I've shown you in the first example, I've shown you a liquid crystal producing topography. In the second, I've shown you a liquid crystal kind of changing its shape. In the third example, I'll show you a situation where a liquid crystal can actually deform something else. In this case, it's going to be like an elastic film immersed in the liquid crystal. So it's going to be like a deformable shell embedded in the elastic host. And the way that these are made is actually pretty cool anyway. This is my collaborator Linda Hurst at UC Merced. She produces these by a process where she has a phase transition from the isotropic to nematic phase. And as this happens, what happens when you undergo a phase transition is, initially you're in the isotropic phase. There's nothing, it's spatially uniform. It's a first order transition, so you nucleate bubbles of nematic phase. Then bubbles grow and they connect, and eventually they replace the isotropic phase. That's what the phase transition looks like. What Linda does is she adds to this system nanoparticles that are dispersed in the liquid crystal. In the isotropic phase, this is the situation on the left, they're uniformly dispersed. As we cool the system, it turns out that the nanoparticles kind of want to remain in the isotropic phase. So they're swept aside by the phase boundary. And what happens is, as the isotropic phase recedes, the nanoparticles became kind of increasingly agglomerated into the remaining isotropic bubbles. They form a solid film. Eventually, the isotropic actually in the middle is replaced by nematic, and you end up with these very cool kind of nanoparticle shells. They are kind of, the nanoparticles are kind of bound together. They're sticky, so they form like an elastic film. And what then happens is the nematic kind of deforms them, and we get all sorts of interesting shapes. They also chain together and elongate. So that was a nice paper of theirs some time ago. We have a PhysRev E where we kind of solve this problem. So you can see the energy functional is now is getting more and more complicated. Now we can do the surface tension, the anchoring, the elastic energy. We also have to put in like a bend energy for the elastic object, lots of constraints, volume constraint, director constraint, and we can minimize that. We can identify dimensionless parameters that kind of tell us the strength of these effects. And I'll show you a movie of the minimization happening. So, we're minimizing all of these things, the director configuration, the shape of the shell, and we get to a nice equilibrium structure. This is not a real one. It's just kind of a low res one just for the purposes of visualization. But you can see we come to a nice equilibrium, even in this relatively coarse case. And then we can characterize how the properties of the material affect this. So like, we get more deformed shells if we lower the surface energy. If we change the bend energy, we get more rounded or more pointed shapes. And we can compare with we can make a simulated microscope image and see how that compares as well. Another thing that we can do, because again, we're not restricted to topography, to a particular geometry, is we can actually see how the shells might interact. So here we are going to minimize, we've put two shells in the medium. We're going to let the computer find their equilibrium position. So I'll let that run. Again, it's just minimizing the energy, following it down the gradient. And, our automated Mesh refinement, I didn't talk about that much, but that's kind of the secret sauce here. Allows it to find an equilibrium configuration. It predicts a chaining angle that is very good, it's very close to experiment. And the other thing that we can do is we obviously started off, here I started off with some particular angle. We can show it started off from many different angles, and we can check that we get the same, it reaches the same minimizer. The only exception is actually if they come about head on, it's a bit like a dipole-dipole interaction, so they have the possibility of kind of ejecting each other. So that's one case where they don't do that. But for the most part, they reach the same uniform chaining angle that's pretty close. I mean, it's within the experimental, it's within the experimentally observed angle. It's quite hard to characterize these systems because there's a lot of kind of heterogeneity, but not so bad. We also find that chaining angle doesn't really depend on the size of the two shells. So I think this is a great place to kind of stop and sort of, I hope I've given you a flavor of my group's work, through one kind of fairly detailed example and two kind of shorter sketches. I've talked about the spontaneous topography, which I think is really exciting. It's a new mechanism. But also, we can look at things like liquid crystal droplets or tactoids. We can look at, the shell elongation and the chaining behavior. If we have like a deformable object immersed in a liquid crystal. And powering all of this is that I didn't really talk about this, but I could give a whole other talk. It would be very, it's kind of something I generally talk to applied math people about because it's really about finite elements. But we have a method that regularizes these shape order optimization problems and makes them much, much easier. So I think, I hope I've convinced you really of the utility of the technique. And this is, I think, exactly where I will stop, other than to say I want to thank, a bunch of students who did this work together with myself. I've had the fortune of working with applied mathematicians to make this happen. There's a lot of very technical work kind of behind it. And I also have the great pleasure of working with really amazing experimentalists, particularly Linda Hurst and Andrea Rodati at UC Merced, and Chuck Rosenblatt and Andrew Ferris at Case Western Reserve. This is funded by the National Science Foundation of the United States, and also by a private foundation called the Research Corporation for Science Advancement. So with that, I'll thank you so much for the opportunity to talk to you, and invite any questions at all. Thank you so much for your time.
Right. Thanks very much, Tim, for an exciting presentation. And are there any questions now? Okay, so if you wish to ask a question, please raise the little hand. Do we have any questions? Hello? Any questions, anybody? Right, maybe I can start with a well, it's more like a comment than a question. But Tim, I was very interested to see that you could actually predict these surface topographies and that they can be actually measured, because this was something I had been led to believe couldn't happen because of the relative magnitudes of the surface tension and anchoring terms. So let me just ask you a question. Do you get the results that you do get for reasonable relative magnitudes of surface tensions and anchoring energies?
Yeah, this is a very good question. So I think there are sort of two key things here. The first key thing is that these are very, very thin films. And this in itself is essential for the effect to work. Like you can't, as soon as you go to something that is higher than a micron, it's not going to work. Okay. And the second thing is that there's a, what I think is happening here is that, you know, we're well above the Smectic order, but no, we're well above the Smectic phase, but nonetheless, there is Smectic order at the free interface. And this is effectively increasing the anchoring energy. That is, I think, basically what's happening.
All right.
So in a sense, this is this is an approximation of a more complicated effect, I would say, that is still to be fully characterized. But nonetheless, like, you know, the predictions are pretty, I think, are pretty striking. So the answer is yes, they are, you know, they're consistent with you know, what we understand to be happening. So they don't, for example, like if you had a micron-sized bubble of normal liquid crystal, of thermotropic liquid crystal, you're just going to be spherical. You know, like, unless you were to do something clever with surfactants to reduce the anchoring energy. But so it's a good question, but I hope that kind of at least gives you a sense that yes, it's not, you know, there's nothing implausible here.
Okay, very good. Okay, questions, anybody? Well, don't see any raised hands, so let me ask another one. You mentioned right at the beginning that the surface tension, like the nematic-isotropic surface tension of a liquid crystal, well, in principle, it should be anisotropic, but we don't really treat it as such, do we? This is a problem that my former supervisor, Tim Slukin, comes back to with me every now and then, but we've never done anything about it. And just wondering whether you know of someone who has. Has anyone actually derived some anisotropic form of the surface tension for a liquid crystal?
I'm not aware of it, and I something I would dearly love. So I need to give Tim a call at some point. Actually, I know he and I definitely we do talk periodically, but it's not something I know of. I mean the other thing that's sort of a bit that's missing here is that similarly we don't really have, I think, a good anchoring model for smectics either. So there's still, you know, despite the fact that loads of work has been done on anchoring, it's a fascinating and complex effect. You know, I think there's still a lot to learn, actually. So.
Okay, very good. So, any more questions from the audience? Do we see any raised hands? Come on, guys, don't be shy.
Maybe I can ask. Hi team, nice talk. So this your last part about tactoids and its objects of changing shape. Are they always? Do you always do it in 2D numerically? Do you expect?
Oh yeah. Yeah, good question. So for the examples here, they were all 2D, but yes, we can do 3D. I should have put some of the more recent stuff, but yeah, we can do 3D. It's just more computationally expensive, you know.
So, but do you observe some shape deformation which are not axisymmetric, or some perturbations which are more interesting?
Well, one case that is very interesting that I have some undergrads working on at the moment is if you put a cholesteric liquid crystal, that is one that has chirality, and you start looking for you know, minimizers of cholesterics in bubbles, yes, you get a whole zoo. It's really what I can say, and I just wish that work was a little more complete so I could show it to you. But yeah, that's one thing you can do. There are you know, there are other things that you can do if you are willing. You know, another thing that we have started looking at is a coated, like imagining like a liquid crystal coating on a colloid, like, you know, patterning the interior colloid, you know, like a Janus particle. So that too can produce very interesting shapes, in principle. So that's another direction we've gone. I think there are millions of others.
For this last topic, it's like liquid crystal shells on a spheres, right?
Yeah, that's
okay.
What I'm thinking about. Yeah.
Okay, thank you.
Well, thank you. Thank you for the question.
Okay, any more questions from the audience? Then maybe I can ask one of a slightly more technical nature. Well, this is all Frank-Hussein theory. Am I right?
Yes. Yes.
Okay. How do you get rid of how do you handle singularities? I mean, you got to do away with them somehow.
So the great news is that we are cheating completely here, right? And the reason that we're cheating is that the geometries that we are considering here, all of them, I'm just going to pull up, I guess I can just pull this, all of them, the defects are virtual.
All right.
And so the defects never show up in the computational domain. They're merely kind of there. So we are very fortunate in all of these geometries that we are interested in that this is able to work. However, it is obvious and necessary to ask the same, like it's obvious that you can construct, or maybe it's not obvious actually, but it's possible to construct situations where that you can't avoid that.
Okay.
And then you absolutely have to use Q-tensor. The good news is that our code, our finite element code, can absolutely handle Q-tensor stuff, and this is another thing that we are presently working on.
Okay.
Yeah.
Okay.
So here we're just lucky we avoid the problem.
Right. Okay. Any more questions? No. So may I end up with well, perhaps a suggestion for you. This picture you've got on now, well, it sort of assumes that your liquid crystal building blocks are rod-like. Could you do this for plate-like building blocks, and would you then get some well, wild and wonderfully different shapes for your tactoids and maybe your shells?
Yeah, I think that's a very good suggestion, and I think all we have to do is kind of put the different elastic constants in, to map that out. But yeah, I think again, it's something we would love to try. And over the coming, our code is already open source actually, and available. Over the coming couple of years, we have a grant to kind of make it easier to use. So, if people are interested, find themselves having a shape optimization problem, this is a resource that I hope people might reach out to us, and you can get advice and support in using it. So if people are interested in these questions, they can also try it as well.
Okay, thank you. Very good. Any more questions from the audience? I don't see any raised hands, so I think it's time to wrap up. Okay, Tim, thanks very much for a very interesting seminar and a very lively discussion. And thanks to everybody for coming, and we'll be back next week. Okay.
Thank you for the opportunity to talk to all of you, and don't hesitate to reach out if you have any questions or as you think about. So thank you. Bye.
Thank you, Tim. Bye-bye.
Okay.
Thank you.
Recording stops now.